Today we are going to solve the truss problem on MATLAB. First we will discuss how we are going to work on it, the strategy to solve the problem. So first we will take the inputs in the MATLAB code that are like area of cross sections, Young's modulus, and the coordinates. Coordinates, like it can be a problem such that let us take this example we will work on. So the coordinates of these nodes, so we will take it as an array, as a matrix of nd cross 2, where nd is the number of nodes. So these are the number of nodes 1 2 3 4, and we will also take this member connection, like where we will establish the connection between the members, like one is connected to 2, one is connected to third node, and one is also connected to the fourth node. And similarly, like second node is also connected to the third and fourth node, and third node is connected to the fourth node. So we will all take these member connections. So this will be equal to, the length of this will be equal to the two like number of element cross 2, as these are these 1 2 1 3, and this will be like we will get this matrix, and we will establish the connection between the members, and these are the like number of elements, and number of these we will like put as an input. And then after this we will initiate the stiffness matrix, global stiffness matrix. Then so we will use the for loop for this, which will run for the number of elements in the in the problem. And so like here first what we will do is we will define the nodes, like node 1 node 2. So let us take example for the first element. Like this is the first, if this is the first element, so this is node 1 and this is the node 2. So when we will connect this, we will need this information, that number of element, like which element we are working on. So this is first element, so we need this node and this node. So how we will take it? We will take it from this connected members, node 1 and node 2. So we will take the first, that is I is equals to 1 to any. So we will take this first, and first row of this member connection matrix, and the first part, like first column part of the member connected matrix will be node 1, and the second like column will be the node 2. So from here we get the node, like this node and this node. So what will this help is, we will now get the location of coordinates from these nodes. This is node 1 node 2, so we will get the coordinates, and from these coordinates we will get the length of that member, and also the sine and cos values. And therefore after getting these values we can easily create the element stiffness matrix. And so after creating this element stiffness matrix, we will update it into the global stiffness matrix. So the indexing will be like, so as we know, like as we know that for any matrix we have to update it, like this is 1 2 3 4 5 6, like 1 2 3 4, so we will add 8. So like similarly here, so we will have to update, like for the first element we have to update it here. So the concept is, we will use like node 1 like 2 into n1, like this is node 1. So this will give us node 1, like for node 1, so this will give us this 2 value, and when we will subtract 1, so we will get here to the x part of it. And so for the y part we just have to 2n n1, and for this, these similarly for this second like second node parts, we just have to multiply 2 and 2 minus 1 and 2 and 2 just. So this will give us the locations of these where it has to be updated, the local stiffness has to be updated. So we will like, so here we will end the this loop, and after getting the global stiffness matrix. So just like now the problem gets simple. We have the global stiffness matrix. Now we just have to find these displacement vector. So some will be known and some will be unknown. So this is just like we will create a vector, and then we will solve it for like k inverse of k into f vector. So this will give us the unknown d. Some will be like known or zeros, which will be like fixed part. So once we get these d vector, we are like, it is very easy. Then like we just need to find the deformed shape. So for the deformed shape, so for the deformed shape, like we need like the nodal locations x1 y1 x2 y2. So first we will need these locations. We actually have undeformed coordinates here. Now we need deformed coordinates. So for these deformed coordinates, what this is a vector, like this is like a vector. So we have to convert into nd cross 2 matrix. So first part this like first element is x component, second is y component. So we will get this deformed shape. After getting this deformed shape, we can like, this will be just the deformed one, like what the deformation is, like displacement. Then we will add these original coordinates to this deformed coordinate, like deformed like displacement. So we will get the like deformed coordinates. So after getting the deformed coordinates, we will just plot these xy values and the undeformed and deformed both, and then we will get some plot of it in MATLAB just by using the plot function. So just by using the plot function. And after this, we for the stress is like, to find the stress, it is very easy. You have to just run this loop till L, like similar for the K till L. So length of the member, then you just length, and then this sine and cos values, and then you just need like u is equals to this transformation matrix into d. So this will give us like the local in the local coordinate system. So d, like, so what the this d is in the index, like the index is similar to here what we have defined in the like this index 1 to like this part. So for the stiffness matrix, it is like you have to update the columns and rows both. But since d deformations are just a vector, so we just have to like update it like index only. So after getting this index, like this t into u, and you will get this u. So then strain is equals to u2 minus u1. This will be like this will be a vector of 2 rows. So you just have to like 2 u2 minus u1 divided by L. So it will give this strain, and when you will multiply it with the Young's modulus, you will get this stress. So here it will complete your problem. So in this case, we are going to solve this problem where we will be solving this. So this will be 1 2 3 4, like, so this will be like 1 2 3 4 5 6 7 8. Then we will solve, like, these are also connected. We will solve this problem. Okay. Okay, so now we are on this MATLAB part of the program. So here you can see in the line number 6, number of elements, like this NA is the number of elements, as I have already shown you the problem. Here the number of elements is 6 and the nodes are 4. Like it is a square kind of truss where each element is connected to the 3 elements. So I have like already shown you the problem where it looks like this kind of. So here this is like number of nodes is 4 and number of element is 6. So now we will move forward. So this area of cross section and Young's modulus as input, then this L is like, this will show us the coordinate location. Okay, I have to create it once again. Like, so this is this L. Okay, so this is L for this problem. So okay, now you have this coordinates 0 0, like the node 1 is at the 0 0, like x 0 y 0. Node 2 is at the x is equals to L and y is equals to 0, and node 3 is at the distance L, x is equals to L and y is equals to L, and node 4 is just above the node 1, which is like like x is equals to 0 and y is equals to L. So here I think you can, as I have already shown you in the problem, so it is quite simple to understand this. Like, then we will move at the nodal connections. This is very important, you need to understand this very well. So node 1 is connected to node 2, 3, 4. So node 1, 1 2, 1 3, 1 4, 4 3, 4 2, 2 3. So this is, now I think you, like you will get this. So now after this member connection, we will like to define the global matrix, like zeros into number of nodes at twice the number of nodes, like it is a square matrix. Then we will like the near node, like for this, like near node is like, here you can see this in M matrix you can see like 1. So 1 is the near node, like, so for M I, like for I is equals to 1, this will be 1, I is equals to 1 1. So M I 1, M 1 1, which is 1, and M I 2, which is 2. So this will be far node. Now we have this will help us very much. So we have these nodal locations. Now as you know, we have nodal locations and we have the coordinates of each node. From these coordinates of each node and the nodal location, so from nodal location we will get the coordinate of each node, and these coordinate will help us get this length of the matrix. So this is C n2 1. So what are this, like n2 is like, we know that n2 is like 2 for the first iteration, so 2 1. So C 2 1. So C, like second column, second row, first, so L, so L minus 0, like n11, n11 is 0. So we will get L square plus, so this will get us the length. So you know x2, this is nothing, just x2 minus x1 square plus y2 minus y1 square, then under root, whole is under the root. And so similarly we will get this sine and cos values. Like, this is nothing, for sine values you have like this x, like this y2 minus y1 upon L. So y2 minus y1 upon L, this will, like this L is for the member length, not the whole length that we have initially gave like. So this is member length, so this will give us the sine value and then cos value. Similarly, like cos value is like x2 minus x1 divided by L, this n1 and n2, like node 2 minus node 1. So x2 from the node 2, x1 from the node 1, and these values are taken from the coordinate matrix. So node 2 we have this value like L, so for the as cos value like L minus 0 divided by L, so this will give us like 1. So now now like, so like as you already know, this is the like K for the element stiffness matrix, like this is the equation, like this is how the equation looks like for the element stiffness matrix. So this is just nothing, this is just an equation. We have got this cos values, sine values, and A and L are constants, like these are the member properties. So now we have to get these index where it will be updated in the global stiffness matrix. So this index, as I have already shown you in the on the paper, how it will be updated, like 2n minus 1, like for the first one 2 into 1 minus 1, so this will update it at 1, then this is 2 into 1 1, and then for the node 2, like node 2 2 2 2 4 minus 1 3, and then this is 4, so 1 2 3 4. This will repeat again and again as this is like nodes will define the where it will be updated. So this is nothing, this just updation of the global stiffness matrix. And after this like we will define these displacement vector and force vector. So this is simple, I guess. Then we will get this where the then the location, the node, the direction uh, where the force is acting. So at the eighth node, okay, at the eighth like the y direction of the fourth node, so we will get the value. And then okay, so in the this f vector we will update at the eighth eighth point, like it is an array, so we will update it there. So okay, after this we will then we will also have this unknown displacement indices. As you know, I have already shown you the problem where the second node is the roller support and third node is the pin joint. So at the pin joint the forces are like the zeros, like displacement are zeros, and at the roller the horizontal will be zero, as this is an horizontal reaction is there. So therefore we will get this displacement indices. And okay, so after this we will like solve this for the displacement, this k inverse. Okay, I think this is something wrong with it, but it is like k, it is k inverse. Okay, it is like k inverse f into f. Displacement like kd is equals to force, therefore d is equals to like k inverse f. Okay, so okay, then we like we just have to use this k inverse function, inverse of this k, this will be multiplied. Okay, now it is good to go. Okay, so this will give us the displacement. So after getting the displacement, okay, we will also like we will update this, and then we will get the original like all the reaction we can get it just from k into d. Now the k is known, d is known, we can get the unknown f force. So deformed shape, for deformed shape, as I have already told you, like this will like xy x1 y1 x2 y2 x3 y3, therefore like we have to get this displacement vector converted into n d cross 2. So I have defined it, and like so the x part is 1, y part is 2. Like in the deformed like df I, like 1 1 is x1, 1 2 is x2. No, not x2, it is a y1. So it will be x1 y1. So first row is x1 y1. So like this will give us the deformed like deformations. So when we will add this deformation into the original coordinates, it will give us the c deformed, like the deformed coordinates. So like now we nothing, it is nothing to do, like now just we have to plot this. For plotting like this number, we will like go for a for loop for the number of element, as we have to like plot for the each element like x1 y1, like okay. So for this member like x1 is cmi1, like member like I is equals to 1 1 1 m11. So m11 is 1 2. So we will get this m111. So for the first member x1 we will get, and then we will get the second member of the node connected, and then similarly for the y1 y2. Then we will plot this will give us the undeformed coordinates. And for the deformed coordinate, we have already defined these deformed coordinates, and we will similarly plot this for the deformed coordinate. Now stress and strain, these are the vectors. So we will define, we will first initiate zero vector, so to save the space, and then we will start a for loop similar to the it is quite till here, till this part. It is like the same as the stiffness one. We just have to use this transformation matrix cross the d index matrix. So this will be like 1 2 3 for index matrix, 1 2 3 4. So d 1 2 3 4. So d 1 2 3 4 will give us the node 1 and node 2 in the global. So we have to convert it into the local. So cs 0 0, and then the second row 0 0 cs, like cos sign. So we will get these u in terms of the global. So now we just have to this this is this vector is like 4 size of size 4, and this is like 4 cross 1, and this is 2 cross 4. So 2 cross 4 into 4 cross 1 will get us 2 cross 1. So u2, then we will get these u's, and after getting this displacement we just have to, after getting this displacement we just have to get this strain, which is equal to u2 minus u1 and whole divided by l. Okay, this is whole divided by l, not just u1. Okay, okay, then we will get this. Okay, we got this this u2 minus u1 whole divided by l. So this will give us this strain, and then stress. Similarly, stress is equals to strain into Young's modulus, and we will get these values. Okay, let me run this. Okay, so we got these stress and strain values, which are quite good for the problem. This was previous run, and we got this plot. Okay, we got this plot also. So this is how the problem looks. Okay, we will meet in next video. Thanks for watching.